you hear me?
Yes, I can hear you.
Okay. Hi, how are you doing?
Yeah, great. Nice to see you.
Yeah, you too. Let's try to see if you can share your presentation.
Okay.
Welcome everyone to the first of hopefully a series of many stellar seminars. Today we have Dr. Peijin Zhang, who recently obtained his PhD from the University of Science and Technology of China. He has worked on solar radial observations and modeling for his dissertation work. He has worked with Dr. Pietro Zucca at Astron, and he will be joining us hopefully very soon at the Institute of Astronomy in Sofia in Bulgaria. The title of his talk is Observation and Wave Propagation Simulations on the Source of Solar Radial Bursts. So without further ado, I give the floor to Dr. Zhang.
Yeah, thank you. Thank you, Carmen. And let me share my screen. Okay. So can everyone see my screen? It is working?
Yep.
Yeah, thank you. So, hi everyone. It is my honor today to give this, first of all, stellar seminar. The title is Observation, Modeling, and Wave Propagation Simulations on the Source of Solar Radial Bursts. So in the content of this seminar is included in three major parts. The first part is introduction. The second is the major part, including all of the works I've done in the past 5 years, including automatic recognition and forward modeling of the solar radial bursts, and the study of duration of solar radial bursts, and observation of fine structures with LOFAR, which is done with Pietro Zucca at Astron. And last part is simulation of the wave propagation effect of the solar radial bursts. And finally is a summary and some future work. So the solar activities have large impacts on the Earth. Solar storms can cause hazards on the space environments. So we need to study the solar activities, and intense solar activities can accelerate the electrons, and the energetic electrons can generate active radio radiation in the solar atmosphere and interplanetary space, which means the brightness temperature can be extremely high to 10 to the 5 Kelvin. It's way brighter than the thermal radiation. So it's non-thermal, it's generated by energetic electrons. And solar radial bursts can provide a unique perspective for space physics research, because it can help obtain a more complete picture of the energy release process. Apart from solar radial, not another wavelengths can see the whole process of the acceleration and the pacing in the solar atmosphere and interplanetary space of the electrons. So we need to study the solar radial bursts. The solar radial burst is categorized originally in 5 types. It's a famous paper by Dock. He first observed the solar radial bursts and divided it into 5 categories, and the type 1, 2, 3, 4, 5 radial bursts. as the resolution and the sensitivity of the radio telescope is built, we can see more detail and in high resolution observations with higher time resolution and frequency resolution. So we can see more compact structures in the dynamic spectrum, like S-bursts. It's discovered after these 5 categories. So today I will majorly talk about type 3 radio bursts and the type S radio bursts. So there is a major problem in the solar radio physics, which is how the radio bursts are generated. Is it generated by plasma emission or electron cyclotron maser emission? So the problem is both of them can provide self-consistent interpretations for a lot of phenomena. For example, this type 3b, 3 pair radio bursts, it's type 3 fundamental and harmonic pairs. It has fine structures in the fundamental part. But the fine structures is not very obvious in the harmonic. The plasma emission gives the explanation of the modulation of beam plasma interaction in turbulence background. So the flux is brighter in the overdense region. And electron cyclotron maser can also give explanations, which is the modulation of frequency ratio. The frequency ratio means the plasma frequency over the cyclotron frequency. So this is an essential parameter in the electron cyclotron maser emission. Also, there are some other phenomena, something like co-spatial of fundamental and harmonic in the same frequency, and the solar size and the visual speed. These two emission mechanisms both can provide the explanations, but we do not know which one exactly is the emission mechanism. They are quite different in the source excitation region, but we do not have in-situ observations. So we need more dedicated remote sensing, like using LOFAR to observe the fine structures of solar radio bursts to further provide constraints on the this problem. So to solve this problem, I've done 4 works. So first is the statistics and modeling. It's automatic recognition of solar radio bursts, and for the modeling of interplanetary type 3 radio bursts. It is to obtain more information from existing data, and the second is observational analysis on the duration of solar radio bursts, type 3 solar radio bursts, and the observation of fine structures with LOFAR. And the last part is with propagation effect to build connections between the observed feature and the real physics parameters. So the first work is automatic recognition of type 3 solar radio bursts. Why I've done this work is because the data size is huge and increasing. And we want to know the systematic property of electron beams. So type 3 radio bursts can do that, and we need a lot of events. So we use automatic recognition method. We developed an automatic recognition method to collect the type 3 radio bursts in non-safe decameter array. So This is the data flow chart, and from raw data to so first the pre-process eliminating bad events, and identify the time where the type 3 diversity is, and further extracting the information like frequency drift rate and starting end frequencies or other informations, and use the information to analyze deeper physical parameters. So this is the result. The most simple thing we can get out of this tons of events is the event rate. Of course, there are more events at solar high year because the sun is more active in the solar high year, and the interesting thing is there are more events detected at summer and more events detected at noon of local time. Because for non-say, the local time is pretty close to UT, so here it's UT. So we see this problem is due to the ionosphere absorption and reflection. Because in the non-say decameter array observed in the frequency range of 10 to 80 megahertz, it's pretty close to the reflection frequency of the ionosphere, which is 8 megahertz. So this is a previous simulation, ray tracing simulation of the wave of 11 megahertz. The wave of 11 megahertz propagating through the ionosphere starting from Earth. So some of them get reflected. The wave gets reflected is measured from the low elevation angle. So the ray path of smaller elevation angle will experience more absorptions and more a thicker ionosphere. But with higher elevation angles, for example, like 90 degree, it will directly pass through this ionosphere. So less absorption is implemented. So in this case, with higher elevation angle, the wave is less absorbed. So the weaker events may be detected in this higher elevation angle, but not be detected at this lower elevation angle. That's the case. So another thing we can get is the frequency drift rate. So it's obtained by fitting the frequency drift line. So for solar high year, we have a very weak trend of larger frequency drift rate at solar high year, but we do not see significant variation in months from January to December. Another thing we can do is to fit the frequency drift rate to this equation. The fitting result is expressed as this. And we also show some previous works like metal, magnetic. It's pretty consistent with some of them. And the most interesting thing about this work is when I fit this frequency drift line to get the acceleration. The acceleration is the median value of the acceleration is positive, which means it's accelerating upward in this range, which is very interesting. We all know in the interplanetary space, it's decelerating. But if this statistic is true, so in the lower solar atmosphere, it's accelerating. But we are not sure where the velocity peak. Which means the acceleration stops and the deceleration starts. This is very interesting to find out when Parker Solar Probe goes to the very near of the solar atmosphere to find out where this electron acceleration and deceleration cross point is. So as a summary of this first work is majorly we have built an algorithm to identify type 3 radio bursts and do statistical works on the information extracted from this 6 years of data. And the statistical results shows that the telescope is more sensitive to high elevation angle of the sun. And the fitting results of the frequency drift rate, and the frequency drift rate doesn't have significant variation with time. And also the most interesting result is there may be acceleration of events in the range of 2 to 5 solar radius. And this is the second work I've done is for the modeling of solar radio bursts. First, the background is there are already positioning methods for solar radio bursts in the interplanetary space, which is the gonio polarimetry. But the gonio polarimetry requires specific instrument and inversion methods. So that was pretty hard. So the objective is to obtain the position and the electron beam track information directly from the dynamic spectrum. Because the dynamic spectrum is the most common data we can get from the spacecraft. So the method is to build build a model of interplanetary solar type 3 radio burst and use forward modeling to estimate the property of the electron beams. So this is the mathematical description of this model. It's pretty simple. The beam electrons is simplified as a point going along this track. The injection of electrons have 3 parameters: the starting time, the direction, and the starting velocity. So there are 3 parts in the arrival time of this radio signal. First part is the motion part of electron beams arriving at a given height, exciting a given frequency radio waves. And the second part is wave propagation part, and the time of wave propagation from this wave generation point to the spacecraft. And the this is the third part. So this 3 parts: starting time, the motion part, and the wave propagation part defines this a relation between the frequency and time. The relation between frequency and time is the frequency drift line, which we can see as this line is the arrival time, the frequency drift line. So we have a model and we have the observation. The next thing we do is to modify the parameter of the models to make the model more and more close to the observation. So we have defined a loss function of the model observation, which is basically the distance between the observation and the model. And by minimizing this loss function, we can get the best estimation of the starting time, the starting angle, the angle of beam electrons, and the velocity. So these 3 parameters can describe when and where and how fast the electron beam goes out of this solar atmosphere and goes into the interplanetary space. The minimization method is particle swarm optimization. So we use this. Yeah.
Sorry, can I ask a question?
Yeah, please do.
If you can go 2 slides back, where does the equation of motion come from?
Equation.
One more slide. Yeah. Yeah, here. This S of R.
Yeah, SR is the arc length of this trace. So
Okay.
it's the integration of along this Parker spiral, the arc length of this. Yeah.
Okay. Okay. So it's basically a spiral arm.
Yeah, spiral arc length. Yes, and so which means the length that an electron beam goes. So divided by the speed of this electron beam, we get a motion time.
Okay,
yeah.
thank you.
Yeah. So please ask questions now whenever you have one. And also there's a page number. If you want to ask all the questions at the end of this seminar, you can remember the page of this where the question comes out. So where were I? Oh yes, I use this tool set on a few events which have determined source positions and associated active regions. First event is this one. It has the source position of only one frequency, which is 4 to 5 kHz, and it's towards this direction, and our model can give a complete track. It is towards this direction. Yeah, so it is consistent. And some more events. This is an event with known flyer set or active region, and our model also give a consistent direction. Yeah, which is on this direction. Yes, this is the multi-frequency observation of this event. And another event is a known active region toward the backward of the Earth. But this event is pretty nice that we have most separated positions for these 3 spacecraft. This is the most ideal position for this 3 spacecraft to observe a single event. If in this situation, we can give pretty nice estimations on the track of the solar radial bursts, the beam electrons. Yes, it's a EVI observation to identify the direction of active region. It is consistent with our modeling. Another event is local emission, and from our estimation, it do passes near the Earth, so it may create local emissions like this. So for implementation, I have made this tool set, including a GUI to click on the dynamic spectrum to get the leading edge, and also it has 2 versions: one MATLAB version, one Python version. It can a very nice part of this this tool set is that it has very nice scalability. As you can see, in the original paper, we use stereo A wind and the stereo B, but it can easily be adapted to wind, stereo A, and the Parker Solar Probe. And in the future, the Solopter and something else. If we have tons of spacecrafts surrounding the sun, all have radio spectrometers giving us this dynamic spectrum, we can get a really precise estimation of where the electron beam is. I'm pretty interested. I'm pretty excited about this project. By the way, I open sourced the code. It's available at my GitHub account. Okay, so summary of this work, I proposed a for a modeling method which uses the leading edge of the type theory bursts in multiple spacecrafts and estimate the parameter set of T0 starting time, position angle of this event, and velocity of the beam electrons. We developed a software to optimize this for the modeling process, and it can show pretty good precision for single and clear events, and also in large separation angle for spacecrafts. When the spacecrafts are very close, so it cannot identify the time difference. So the time difference in this project is essential.
Peijin, can I ask a quick question?
Yeah.
This T0, is that the time zero for the starting frequency for which you're estimating the position,
no,
or what
it is sorry, and I didn't explain very clear. The T0 is where the time zero for the starting of beam electrons at the solar surface, and the theta zero is the position angle at the solar surface. So all starts from the time reference is the release of beam electrons from the solar surface.
Okay, and then theta zero would be like the heliolongitude of some sort. What is it relative to? What is the theta
relative to the Earth sign line? Yeah, and the velocity is the velocity along this Parker spiral. The third work is to study the duration of type theory bursts. Because we have several factors that can contribute to the duration of solar radial bursts. First is the velocity dispersion, and the second is horizontal density difference, and the third is wave propagation effect. The motivation is try to confirm the major factor. So we use low-field imaging and spectroscopy to investigate the source position at different time and frequency, and quantitatively analyze the contribution of these factors. So this is the event. It's a pretty huge event, but we do not focus on the major part because it's too bright that it saturated the LOFAR. But fortunately, after the major event, we have some small type series. One of them is looks like this. It's very single and clear, and it has a duration of about 3 to 5 seconds. After this, I will briefly introduce the factors that can contribute to the density, contribute to the duration. First is the density difference. Because as you can see, there are many fiber structures. These are density differences. There are huge density differences horizontally. So, for example, in this one magnetic field line as a fiber, the density of this R1, R2, and R3 is the same, but they're at a different height. So they're, for example, when the electron beam propagating upward, it arrives R1 first and R2 second and R3, and the all emit the same frequency of radio wave. So the time difference between R1 and R3 is the duration of solar radio bursts. And another contribution is the velocity dispersion. I have an estimation. So there are open magnetic field lines in the solar atmosphere, and we have frequency and the density relationships to have this layer mapped to the frequency channel, and we have released the electrons from this lower corona, and after that they have different speed. So the fastest electrons arrive this layer first, and excited the leading edge part radio bursts, and after that they all are proceeding upward, and the major part reaches this layer and giving the peak radiation, and after that the tail part reaches this layer and emitting this tail part of this radio burst. This is the concept of velocity dispersion causing this duration. So how do I know which kind of factor contributes most to this duration of type radio burst? So basically, I do the imaging, and I do imaging for different time and frequency to inspect. So this is a 2D mapping of the source position. Simultaneously maps the time ratio and frequency to the sources at the same time. And as we can see, the color phase represents the frequency, and the brightness represents a time ratio. So darker points in this scatter plot means later, and red means low frequency, blue means high frequency. And as we can see, the early part and the late part are isolated while, and as predicted from low frequency to high frequency, it's along a path. So if we separate the front edge and peak and the tail edge, it does separate it pretty well. The leading edge looks like the pretty fast portion, and the peak is the medium one, and the tail edge is the slowest one. If we fit this tail edge and the source position, and so this is a 2D fit of the velocity. It has projection effect, so the speed is underestimated, but it already shows very big differences between this three speed, the speed of leading edge, speed of the peak, and the speed of the tail.
Sorry, can I ask a question? What density model do you use? How do you convert the frequency to height?
We do not use density model because this is a direct imaging. From the imaging, we can already have a position.
Oh, okay.
The heliocentric distance is the height. Yeah, this is
right. But how do you determine the front edge, peak, and tail edge from the imaging?
Front edge and peak, and we have this double Gaussian fit at this So for each frequency, we have this light curve, and we can fit this light curve to a double Gaussian. It's basically one and two Gaussian meet the peak part. So one can be very slope and one can be very steep. Yeah, this so
That's
from this
fitting in time.
Yeah, fitting in time, we can get the frontage is always the half maximum of this fitted result.
Right.
So if, but if we
from the spectrum.
Yeah, from a spectra. So if we directly use the peak point, the peak is very not at the center of this. But if we use fitted result, it aligns the center, more pretty. Yeah. So after that, we statistic the time distribution of the source at the same heliocentric distance to measure the contribution of velocity dispersion, and we estimated the horizontal density difference with this equation from previous publication by statistically calculated the density distribution at the same height. And the propagation effect we cannot directly estimate because it is convoluted in the estimation. So we assume it's less than half of the total duration because we find a pretty short-term burst at the same position with the almost the same size at almost the same position, but the duration is very short. So we assume the propagation effect is less than half. So we summarize this previous statistical result is the forward half maximum of velocity and dispersion is pretty close to the observed forward half maximum duration, but the forward half maximum duration caused by the density difference is not as large as its velocity dispersion. So from this, we draw to the conclusion that the velocity dispersion is a major factor, at least for this type theory burst, the duration. Yeah, so we use low-for beamformed imaging data with high frequency and time resolution to find out the determinants of the duration of a type 3 burst. So the conclusion is, so in this frequency channel or range, the velocity dispersion is a major factor. The next two works, which is the fourth and the fifth work, is on the observation of fine structures. So the background is high performance instrument can produce high resolution observations, of course, something like LOFAR. And the short-term narrow band fine structures can represent more isolated physics processes. So we use the method is we use LOFAR to perform imaging spectroscopy for the fine structures in the solar radio bursts. The first thing I look into is solar ice bursts. It's the most, not the most, it's a very short and narrow bandwidth burst. Typical solar ice burst doesn't have fine structures. It looks like this. It happens within second. And the snapshot bandwidth is less than 0. A few megahertz. So it's really narrow bandwidth and short duration. And with LOFAR, we can see fine structures. In order to extract the property of fine structures, I use a previously developed program to extract the frequency drift line. And after I put the frequency drift rate and the brightness together, I find they have very similar trend. When it's brighter, the flux is large and the frequency drift rate is larger. So in the dynamic spectrum is when this frequency drift rate is large, the frequency drift is steep, and it is brighter. Like it's steep is brighter, and when it's not steep, it's darker. So this relation is pretty intriguing. So I propose it's due to the optical depth, uneven optical depth distribution caused by the density disturbance. So when the density is higher, it is more optical thick, and we can see less light. And so in this case, the variation of the density with height is larger, and this can have these two relations can be merged to have this relation. The intensity should be proportional to the frequency drift rate. So we have 1D simulation for this phenomena, and as we can see, it is very consistent with the observation. When it's brighter, it's steeper in the dynamic spectrum. The frequency drift is large, the flux is large, the frequency drift is small, the flux is small. So to summarize this work, we find the fine structures in S-bursts is for the first time due to the high resolution of LOFAR. And the frequency drift rate and the brightness temperature have a positive correlation. When the frequency drift rate is large, in the dynamic spectra, it tends to be more bright. Yeah, please, sorry, I see the right hand. Go on, comment. You have a question? Yeah, so I will continue. Yeah, and this fine structure and the correlation could be due to the optical depths and the variations caused by density fluctuation. The second work on the fine structures is to observe the fine structure of type 3 burst, meaning the type 3b part. So we use the ever used longest baseline, which is the core and remote stations. We don't need the international stations because as that long baseline, it can only cause noise. For snapshots like the solar imaging, we only need the core and the remote. That's the longest requirement. And the theoretical resolution is about 36 arcsecond, and the actual spatial resolution from the fitted beam size is about 150 arcsecond. The time resolution is about 0.167 second. And as you can see, the imaging of the imaging result and the fundamental part moves really fast from the center to the limb of this fundamental part, and the harmonic part is very stable near this active region. So we have extracted this position information and brightness information and source area information from the imaging of this type 3b and type 3 burst. As we can see, In this 3 frame, the time difference is the most highest time resolution, 0.16 seconds. The source moves from the center to the limb within these 3 frames. But for the harmonic part, which is blue shadowed part, the source is pretty stable near this active region within this 6th frame, which means this 6th frame, about a few seconds. So this is a major result. For the harmonic, the source is very stable. The source size doesn't increase that much, and the source speed is very low. But for the fundamental, it's very active. The source area increased from 50 arc-minute square to 200 nanometer square within 0.45 seconds. And the visual speed of the source, fundamental source at 26 megahertz can be 4 times the speed of light. Okay, the visual speed is larger than the speed of light, but this doesn't mean there is any physical part exceeding the speed of light. And the visual speed of harmonic part is less than 0.11 times of the speed of light. So we reckon this could be due to the scattering and the refraction, which means propagation effect dominates this visual speed and high dynamic of fundamental source. So here I want to pose this discussion is about the co-spatial and visual speed discussion. Because for a given frequency, for example, 26 megahertz, the fundamental part and the harmonic part comes from different height. The fundamental part comes from lower height and the harmonic comes from higher part, as shown in this diagram. But in the observation, the major part, the position is very similar for the fundamental and the harmonic. This is problem 1. And problem 2 is the visual speed. The visual speed should be very small because for a given frequency, the region of wave generation is very compact. It's a cross section of the electron beam with the certain layer of density, have density relation with this frequency. But we observe pretty fast visual speed. So this is a conflict with theory if we assume the wave propagates directly from the exciter to the observer, but it's not. There is propagation effect. This comes to the last part of my works, is the wave propagation simulation, because wave propagation have significant influence on the imaging and spectroscopy observation. So we want to build connections between the observation and the physical property of the real source. So the method is we perform ray tracing simulation with an isotropic density model. Before starting the major part of the simulation, I want to say that there's the reason why simulation of propagation effect is important. There is an inconsistency between the theory and observation. One is the source size and bandwidth. For example, in this type 3B burst, there are fine structures. The frequency can be mapped to the electron density with a density model. So with this density model, the frequency limit of these fine structures corresponds to a limit of where the source is generated. it's a pretty compact region. But as we can see from the observation, the source region is very large. It's almost the size of the sun, half size of the sun. So this is a conflict. Another conflict is the visual speed. The visual speed is too large. So we estimate this should be due to the propagation effect. So the imaging and spectroscopy is largely influenced by the propagation effect, majorly the refraction and scattering. The refraction can cause systematic bending of this light path. But in the solar atmosphere, there are density disturbance can cause random walk of the ray path. In this way, this ray path is unpredictable, it's more complex. So we need to emit a lot of rays to statistically analyze this rays to give a estimation of this real source. So the wave propagation effect comes from the density fluctuations. The medium is fluctuated and refractive for the radio wave. So we need to consider the scattering. It's like a black box between the intrinsic source property and the observed features in the imaging and spectroscopy. The propagation changes this property. For example, like the brightness. After propagation, it gets weaker, but to what degree we need the simulation to find out. So we model the propagation process with simulation to study the propagation process. The description of this propagation effect is use a Fokker-Planck description. I won't go into the mathematics very deep. So the isotropic scattering is because, as you can see in the solar atmosphere and in interplanetary space, the density fluctuations is not isotropic. It's primarily along the radial direction. So there need to be introduced a anisotropic matrix to describe this anisotropic density fluctuations, to describe the anisotropic scattering. After introduced the anisotropic matrix into the Fokker-Planck equation, we have the complete ray tracing equation. So the forward step is to consider both the refraction and the scattering. And the scattering tensor includes the anisotropic scattering. So after complete this accelerated code, we put this massive computational task to the supercomputer of USTC and run about a few weeks to get the final results. We can construct the sources from the ray tracing results and the source speed and the source and the area and the source offset and source variation. So after that, we want to compare with the observation. For example, the duration and the size and duration. So if we directly compare the source and duration, this is the source size, and the black line represents the duration. We can have this estimation of fluctuation variance and anisotropic parameter of about 0.7. But as I said, the the duration includes a few factors. For example, the velocity dispersion. So this contribution is overestimated. It should be smaller. So the isotropic parameter should be larger than, should be smaller than 0.7. And we can get the simulation results for the source size and the decay time of harmonic. As you can see, the duration of harmonic is much less than the fundamental. And also we can have the position offset of fundamental and harmonic. If we compare the fundamental and the harmonic, this is harmonic, this is a fundamental. You can see the most part of the fundamental is positive, which means the source is shifted outward. And the major part of harmonic is blue, it's shifted inward. So coming back to the previous problem, which is a co-spatial problem of fundamental and harmonic. And they are pretty much observed at the same position, at a similar position. So from the perspective of propagation effect, it can be interpreted as the fundamental is shifted outward, the harmonic is shifted inward or less shifted outward. So the distance between the fundamental and the harmonic is closer than the geometry distance shown as this black line. So also we can reconstruct we can estimate the source speed, and the maximum can reach 0.5 RS per second, which is very close to the speed of light. And the harmonic, the source speed of harmonic is much less than the fundamental. Also, as to say, the harmonic is less affected by the propagation effect because it comes from a position where the density, where the local frequency is much less than the frequency of wave. So comparing the observation with what we have in the simulation, we still cannot find a parameter set which can reach 4 times of speed of light, visual speed. So there are other factors, something like complex magnetic field configurations and something like this in this to affect the source visual speed, but we need to find out in the following simulation. And also the expansion rate can reach 1 R solar radial per second, which exceeded 1 times of speed of light. To summarize, because this work is huge and it takes a lot of time, it has more results. For fundamental wave, both the source size and decay time increase with the scattering rate. And the isotropic fluctuation can produce larger decay time than a highly isotropic fluctuation, while the source size is not sensitive to the isotropic amplitude of the fluctuation. But for the harmonic wave, the source size and decay time are largely determined by the scattering rate. So we obtained the estimation of scattering rate is this number, and the alpha of about 0.7 for the wave of 35 megahertz. Also, the isotropic scattering can be used to interpret the co-spatial phenomena of fundamental and harmonic wave. The visual speed can reach about 1.5 times of the speed of light. it is not compared to the observed 4 times of speed of light, but it is larger than what we thought with not isotropic scattering considered. So there are still more interesting features to consider, such as the directivity, the eccentricity, time delay, the brightness, temperature, the beefield shape, and so much to consider. So this work is still continuing, and more works are coming out. So stay tuned to our next episode, next paper. So that's what I've all done in the past 4 and 5 years. I have an overall summary of my work. Is I have developed an algorithm to automatically identify type 3 bursts and perform statistical to this event, and do forward modeling to estimate the interplanetary type 3 burst position, the velocity and trajectory, and discuss the duration of type 3 burst and find with imaging spectroscopy and find the velocity dispersion is a major factor. Also, we obtained and trying to interpret the fine structure of solar radial bursts with high performance observation of LOFAR. Finally, it comes out that the propagation effects have very large effects on the imaging and spectroscopy observations. So we study this with propagation effect, use simulation and isotropic model to build the connections between observation and the physical property of radio emission and background plasma. So future work, for the future, there are still tons of imaging spectroscopy data untouched. LOFAR have accumulated thousands of terabytes of data, but a major part of LOFAR data contains very interesting observations, but we need to analyze them. Also, as I mentioned, there are more interesting features to be simulated and inspected. Another thing I want to propose here is polarization and the magnetic field. That's it's not it haven't been very commonly done. So I prepared to put some effort on the polarization imaging and to see what I can do to inspect the magnetic field. Also, if there is a chance of in-situ observation of Parker Solar Probe in the type 3 burst, for example, and collaborated with LOFAR observation, that would be constraining the emission mechanism to a new degree. So I have published about 7 papers, which I covered most of them in this talk. One of them I didn't talk about is this machine learning paper. It's not relevant to the subject, but yeah, this is something I've done in my PhD work. I've open sourced most of my my work at github.com/Peijin94. It contains majorly 4 code base. The first is the LOFAR Sun tools. It contains the data processing and visualizing. Second is to obtain the frequency drift line to get the frequency drift rate. And another is forward modeling toolset. the final one haven't been introduced, but still open source code is the machine learning method to generate microwave image from STO AI image. And that's all. Thank you for your attention. Please ask questions if you have one, and I'm happy to answer any kind of question.
Fantastic. Thank you so much, Peijin. This was a great presentation.
Yeah, thank you.
Let's see, are there questions? If you have a question, please just unmute and ask it, or you can ask it in the chat if you want. And while we're waiting for people to come up with questions, I have a question. So this method that you're talking about, obviously applicable to plasma emission, can this be applied also to type 2 bursts, the method showing you the source location?
Oh,
I mean, obviously we have a lot of fundamental and harmonic emission in type 2 bursts as well.
Oh, yeah,
you applied it on a type 3 burst, right?
You mean the simulation? It is okay. In the simulation, the source is assumed as a single pulse. All the radio waves generated at the same time at the same point. So it can be applied to any kind of solar radio bursts, depends on the convolution. If there are type 3 radio bursts, the convolution should be in a fast propagating out electron beam. If applied to type 2 radio burst, it should be aligned with the shock front or where the wave is generated. So yes, it is applicable to any kind of burst.
Yeah, because you could simulate the type 2 burst as a series of short pulses, right? Bursts of electrons.
Yeah, so all bursts are convoluted from a single pulse. A single pulse can convolute to anything. Yeah.
Interesting. And one more question, if that's okay. So this the fitting of type 3 shapes in the dynamic spectra in your model gives you the onset time on the surface of the sun. Have you tried to compare with activity in AAA or some high frequency observations to constrain whether that T0 that you get is right?
Yes. The T0 theoretically it is where the energy release happens. So yes, it can be used to be compared with, for example, the energetic electron. No. This is the particle flux with the, for example, flyers. When flare happens, there are electrons accelerated, and in these accelerated electrons generated type 3 radio burst. And if I do the forward modeling for this type 3 radio burst and inverted it to T0, and the T0 should be the same as the flare time, at least close to. Yeah.
Have you checked?
Yes, but not exactly the same. We majorly concerned about the trajectory. The time is roughly the same because the time resolution of this what I call is EUVI is pretty low. So
Right.
we do not have high time resolution imaging, the high resolution EUV imaging and to compare with.
All right. Any other questions? All right. These are all very, very interesting things that we've worked on. And I will have more questions undoubtedly.
No problem.
Yeah,
I'm
but
always
I have your
online.
presentation. So thank you very much for this very nice seminar, and we'll hope to see you soon. And if anyone has any questions that they come up with later on, then you can always send me an email, and I can put you up in contact with Peijin, or maybe you left your email. Maybe just write it in the chat.
Oh yeah, I'll leave my email in the chat. If you have any other questions, I'm happy to answer. Yes. Oh, sorry. It's sorry. It's. Oh yeah, the second one is the correct one. So the first one is not correct.